Okay, so I'm going to try to keep the window small here for my Python script, and we're taking a look at homework number 3. I'm hoping you can read the Python uh, script here. So, just a couple things I wanted to note here. Um, Most of the time we'll be using NumPy. Here we'll also be using the linear algebra subroutines. And so if we want to just go ahead and define the x as an NP array, that works. And then phi1 is also, I'd like to define it as an array, although yeah, you can get around that. Um, I'm defining this particularly as a column, right? Good. And then so the rest of this was to compute that norm of the error. Let's see if I can pull that up real quick. Okay, so in number 3 we were looking to compute this error quantity here. And so we have the left side of the equation, then we have this middle term, and then we have the right side of the equation, where this is our matrix X. Okay, so what you're seeing on the left here, these are the column norms, right? So how will we compute the sum of the column norms given this matrix? Well, I think the easiest way to do that is to just sum down, or sorry, first square all the elements in X, and then sum down so that you get a row, and that row, the elements of the row will represent the norm squared of each column, right? And then you would just sum through that row. And so that would be, and then you would take the 1 over p minus 1 here. That would be your left-hand side. So let's see how that might work. I'll have to pause for a moment and bring up. Okay, so I'll show you how to compute the left-hand side. Let's bring it up here. So I'm going to go ahead and take p equals 4. And then what's next? Because we're going to be computing that covariance matrix in the middle term, let's go ahead and mean subtract our data. So how do we do that? Right, we'll take the mean column to be the mean, but remember, this is axis 1. That's because in Python, remember, we start at 0. So 0 would be the sum down, and then 1 would be the sum across. And then here we just take our x minus our mean column. And notice that you have to use this np.newAxis, right? Because the mean column is just going to be, well, let's see what that is. If you, let's go ahead and run these lines here and see what we get. Okay. And so if you take a look at what the shape of the mean column is, or what I'm calling mean col, yeah, you see this empty dimension here, and so that's why you have to have the newAxis command in line 19 here. Okay, good. And then so now what we wanted to do, remember, was to sum the squares of the matrix elements. So how are we going to do that? XM is our matrix now that's been mean subtracted, and so np dot square will square all the elements of your matrix. And so we would say np dot square dot xm for our mean subtracted. And then what do we want to do with that? We want to sum down the columns, so we would say np dot sum, and now we want to sum down, right? So is that going to be the default behavior for the square, to sum down? Oh, actually, what is the default behavior of sum? In MATLAB, this default behavior of sum is to sum down, but in fact the default behavior in Python is to sum all the elements. And so actually that's what we did want to do, is we wanted to sum all the elements of our x squared matrix, so we can just leave it at that. Good. And then finally we have to multiply by the 1 over p minus 1. Whoops, p minus 1. Good. And let's see what we get. 4.83. So when I sum the other two terms together, I should get 4.83. By the way, as a hint, how would we compute C times phi? We would use, now there's two ways you could do it. You could use matmul, and then, oh, we haven't computed C yet. How do you compute the covariance matrix? It's just np.cov. And then it doesn't matter if you use XM or not, right? Because it'll automatically mean subtract. Good. All right. Run out of the page here. Whoops. Let me see if I can. Whoop. I don't know. My window size just got all messed up. Okay, well, how are we going to compute this covariance matrix now? That's the main question we're talking about. It's the phi transpose C phi, and so you can either take matmul, that's what we were saying, or you can use the @ sign. So I'm going to pause and redo my windows here. Alright, so I've got the window back now, and we were trying to figure out how to compute phi transpose times C times phi. So let's just compute one side of that. You can either use np.matmul, and then you can take, your phi transpose and your C. So that's one way to do it. Oops, is that phi or phi1? Sorry about that. That was phi1. Good. Okay, or you could take phi1 transpose and use the @ sign. Excuse me. There you go. So you can see you can get the same result. Excellent. All right. So I will leave the rest of those to you. Now, one thing that people do ask is how do you compute the error part? So what I mean by that, let me pause here for a sec. So the errors here, that's the error on x by using phi1 as the basis vector, right? So it's what's left over after you've projected x to phi1. How do you project x to phi1? Well, that's phi1 transpose, or phi1 transpose, right? phi1 transpose is the projector or projection matrix. And so then you take x minus the projection, and that's what x error is. Did everybody catch that? So x error is the error after you've projected your vector onto the first basis vector. Therefore, x error is x minus the projection of x onto phi1. So it's x minus the projection of x onto phi1. X minus the projection of x onto phi1. Maybe I should. X minus the projection of x onto phi1. Well, okay, onto phi1. Okay, so how do we compute that? Actually, I'm going to go ahead and use the mean subtracted version. So that's just x error equals x mean subtracted minus phi1 @ sign phi1 transpose times xn. Oops. What do you think? Is that going to work? I don't know why I keep that window just bugs me. Okay, so let's look at the shape of x error. What should the shape of x error be? It should be the same size as x, right? 3 by 4. Good. So now we've got our x error, and then what are we going to do with it? What did that say? We're going to compute the same thing over here as we did over here, right? So the same computation applies, And so I will let you finish that off and see if these three things are, if um, this if this equation holds true. That's what you're trying to find. Good. Okay. Um, now, uh, let's see. Maybe I'll stop here for a moment.